Hello, good morning from Indonesia. Welcome to the webinar series of the commemoration of the 100th anniversary of volcano monitoring in Indonesia. I saw many participants coming from multiple countries. Thank you for coming to this webinar. So today we are on the 15th webinar. So we are here. And today's topic will be the Global Volcanology Talk, the past, present, and future of volcano monitoring. And we are 9 days prior to the end of this celebration. And tomorrow we will have blood donation events, and this will be held in Bandung. So for all of you who would like to participate, you can come and donate your blood, and the safety protocol of the COVID-19 will still be applied during this period. So before we start with the presentation, I will show you briefly the history of volcanology in Indonesia. So started in 1919, Kelut volcano in East Java erupted, and more than 5,000 people died. And then less than 1 year later, in 1920, systematic research at volcanoes officially started. And in 1922, it was made permanent. The volcanologist Untersuch became the institution that permanently monitor volcanoes. And by 1941, 11 volcano observatories has been built. And in 1942, the volcanological research were transferred to the Japanese authorities. And after the Independence Day of Indonesia in 1945, the volcanological service transited to the Indonesian government. And then the evolution started in 1963 to 1976. The volcanological efforts were made, and then it was evolved and changed names during the 1978 to 2001, and now started from 2005 to now. It is known as Center for Volcanology and Geological Hazard Mitigation. So in the beginning, volcano monitoring was meant to save lives. And today, Indonesia have 127 active volcanoes. 69 of them are monitored 24/7 by 74 volcano observatories. And today we are celebrating 100 years of saving lives. And the information concerning volcanoes can be seen in this website, magma.isdm.go.id. So in the past, you cannot see the activities of volcanoes as easy as now. Now you can visit this website and you can see all the activities of active volcanoes in Indonesia, and you can have all the recommendations. So before you climb the volcano, before you visit the volcano, please visit this site, and then you make sure that you know what the safety measures that taken by the authority. And okay, let's continue with this webinar. So the Global Volcanology Talk will focus on talking about the past, the present, and future of volcano monitoring. As we know that volcano monitoring has been done for more than 100 years in the world, and it is seen as an important things to do, because by monitoring volcanoes, we could understand, we could study the activities of the volcanoes, and if such changes appear, we could make actions, and then to make recommendations for the public. And today we are very happy because we have 6 world's volcanologists, and they will present each of them 10 minutes, except for Dr. Patrick Allard, who will present in 15 minutes. So the first speaker I will introduce you is Dr. Patrick Allard. So Dr. Patrick Allard is a French volcanologist. He is based in France. At the moment, it is 4:30 in his place. So he is the Emeritus Director of Research within the CNRS. It is attached to the IPGV, or the l'Institut de Physique du Globe de Paris in France. So he is currently the president of the International Association of Volcanology and Chemistry of the Earth's Interior, or IAVCEI. He was elected in 2009, and he will be there until at least 2023. Patrick has a very extensive experience in all active volcanoes around the world. So he is an expert mostly for volcanic gas emissions and magma degassing processes. And we are happy that today he will give us a lecture about the global volcanology, an overview of global volcanology. So Patrick, time is yours, 15 minutes from now.
Thank you very much, Devy. Searching my file. And let's see my. Sorry, let's see my file now. Disappeared. Okay. Thank you very much. Selamat pagi semua. I'm very happy to an honor to be invited to make this talk, and I hope you can see my slide. Is that possible?
I think you can play your slides.
Okay, is that right? Okay.
Okay.
Fine.
Please, Patrick.
Okay, so my talk will be a brief overview of the past 100 years of development of volcanology, let's say, from 1920 to today, more or less. Volcanology 100 years ago was a very stammering new discipline of sciences. There was no teaching, no specific degree, and very few people involved, even though very great, remarkable pioneers in different disciplines. At that time, seismic survey of volcanoes was only, as the map shows you here, only rare stations on the very few volcanoes in the world. But it was already known as a number of features. The first, that eruptions were preceded by earthquakes, that different volcano-seismic events exist in different classes, and that in order to record volcano-seismic events, we needed multiple instruments. As far as regards volcanogeodesy, which is the way to monitor ground formations, this discipline was born at Campi Flegrei Caldera in Italy, near Naples, due to the record by marographs and also visual observations of the subsidence and uplift of the caldera ground. And this volcanogeodesy became, in the 1910s, a monitoring tool developed specifically, in particular in Japan, in Hawaii, with the famous work, pioneer work of Omori in Thomas Jagar. Volcanogeochemistry, which means the study of rocks and volatiles of magmatic rocks and magmatic gassing processes, were in a very infantile stage. At that time, there was a very great petrologist, as Bowen in particular, but most of igneous petrologists considered magmatic volatiles. The volatiles are those components dissolved in the magma that become gas and form bubbles and escape from volcanoes. And they were considered negligible components because they made only a few weight% of magmas as measured at that time. But in fact, a few rare scientists had the early intuition that these magmatic volatiles, being able to generate bubbles and pressure and rising in the magma, could have a key role in volcanic processes and eruption dynamics. The names are here. In particular, the American Frank Perry had studied the 1906 eruption of Vesuvius and was convinced, he concluded gas was the active agent of the eruption and the magma, it's very cool, as seen here. And just to mention you that 1913 in Hawaii, Day and Shepard, sampling gas from Hornitos and the lava lake El Halemaumau crater, discovered for the first time that water was predominating volcanic gas, which today every one of us knows very well. So volcanology, like many other scientific disciplines, developed the consequence of many crises and catastrophes. In particular, here I remembered the events that happened early in the early 20th century, in particular 1902, there were the eruption Mount Pelée, eruption of Sufre and St. Vincent in the Antilles in Santa Maria in Guatemala. And these events made a lot of victims. We also remember the Kelud eruption in 1919. And all these events promoted the creation, the buildup of volcano observatories on the various of these volcanoes, and as Devy mentioned earlier in Indonesia as well, and the creation of volcanological surveys. These catastrophes, and after the First World War, promoted a strong consideration that international scientific cooperation was absolutely required, absolutely needed in those sciences, in particularly in volcanology. 1999, even that just 1 year before 1920, is a real benchmark for global volcanology. That was a year during which was created the international IUGG, the International Union of Geophysics, Geodesy and Geophysics, among which had 6 sections, and the section of volcanology, the ancestor of what we call now the IAVCEI, International Association of Volcanology, Chemistry of the Earth's Interior, sorry. And this early section of volcanology had 4 remarkable leaders, 2 Italians, 1 French, and 1 American. And later on, this section of volcanology became the International Association for Volcanology in 1933, and then IAVCEI in 1967. Developments of volcanology over the last 100 years, I'll make just a brief overview. Of course, there's so many things to say in such a few time that it is not possible to describe everything. Just consider that this has been driven by a combination of scientific curiosity, scientific progress, technological advances, emblematic volcanic events that occurred during these 100 years, and societal requirements. Just show you a few examples of the conceptual advances in the 60s in particular, a major revolution in volcanology, in earth sciences in general, has been the discovery and demonstration of plate tectonics. Volcanoes could be understood very clearly in terms of source of magma, source of volatiles, dynamisms within the framework of plate tectonics. Of course, we all know also of these, the MOGI model that was very important to interpret deformation at volcanoes and so on. Other conceptual advances in the 70s was the development, the application of physical volcanology, quantitative physical volcanology, to study pyroclastic deposits, magma fragmentation, lava flows, volcanic plumes by different authors. And also in the 80s, the development, the application of fluid dynamics to magmas and volcanoes, in particular to understand magma chamber processes, the eruption triggers, and also the instabilities in volcanic plumes or in buoyant magmas. And modeling has been also a step ahead in the 80s, 90s, and more recently, still more recently, using both analog and numerical models in order to compare and simulate natural observations, magma chamber dynamics, volcanic conduit dynamics, plume dynamics, and numerical simulations of observations made at surface, either for the magmatic volatile phase, depth ground formation, seismic signal, and the dynamics of magma ascent as well, of course. Another second important aspect for the development of volcanology in these last 100 years was the progress in technological advance, both for field measurements and in the laboratory for analysis. And this has allowed us to develop new techniques from big to small here, from direct to remote, from intermittent to continuous measurement, from ground to space, and from local to global. From big to small, just give you an example here. For the ground-based UV remote sensing of volcanic SO2 fluxes, the first instrument that was available was the COSPEC, correlation spectrometer. That was an instrument that started to be used in the early 70s. Its cost was around $60,000 US, and its weight was around 40 kilos. And in 2000, look at the same, or not exactly the same mechanism, but the new instrument to measure SO2 flux, that was like a cigarette packet and in size, and $2,000 US. So that was a revolution in terms of technological development for those measurements. Other measurements, other developments were made, allowing, for instance, to track, to analyze dissolved volatiles in glass or melt inclusion trapped in crystals, that allowed, as a function of pressure, to track the decompression, magma decompression path. Also, experimental volcanology in lab allowed to constrain the melt properties and the dynamics of melts, the viscosity, the properties of magmas at different pressure and temperature conditions. And finally, of course, and I'll come back on this, spaceborne remote sensing. Technological advance has allowed, in particular, sophisticated geophysical imaging magmatic systems that reveal much more complex than we initially thought. Magma chamber were initially considered as big bubbles of magma stored in the crust and somewhere, but they're revealed to be much more complex, being a network of seal and dikes and so. And this was a great progress in understanding the roots of volcanoes. That's very important to quantify the magma plumbing system in order to forecast eruptions. The magma plumbing system could also be imaged, investigated by looking at the petrology, at the geochemistry, at the crystal characteristics, that is a nation of crystals having different timescales, as Fidel will develop. We got people got evidence, computation evidence for multiple magma reservoir complexity, and also for the mixing between different types of crystals that attest of magma mixing, longevity of magmatic systems, so very complex processes of death. A great step ahead has been, of course, the advance due to the development of sensors on satellite, spaceborne, in particular for using UV or infrared sensing for monitoring the volcanic SO2 emissions from individual volcanoes and also global volcanoes. And now we have a network of sensors allowing to detect not only huge SO2 clouds emitted during eruption, but also moderate SO2 emissions from, let's say, small eruptions or continuously passively degassing volcanoes. And of course, spaceborne sensors in radar in particular have now currently and widely used to monitor volcano deformations. Today, more than 2050 today volcanoes showing known to show deformations and are regularly monitored from space. This is a major step. So just a brief summary, and at least I can't describe everything, but in these last 100 years, there was a strong advance in the quantitative study of volcanic eruption deposits in the field. That's field geology, field analysis of the deposits to reconstruct the past of volcanoes. A lot of developments in numerical and computer modeling of the physical behavior of volcanoes, magma, and processes. Micro and even nanoscale analysis using up-to-date techniques in lab to accurately data mine the major and minor trace elements and origin of magmas and minerals, the pre-eruption volatile content magma properties, radiological properties. And so a lot of developments as well in remote sensing to measure gas emissions, either in the UV or in the infrared. And of course, detection of precursors, many detection of gas precursors before eruption, changing SO2 flux, in particular, specifically in those residues, the change in CO2 to SO2 ratio with the increase of CO2, the least soluble volatile content in magmas, which start degassing the first and the deepest. And experimental volcanology in lab, also high pressure, high temperature. Of course, a lot of developments in geophysics on the volcanic, the type, the typology of volcanic earthquakes, the imaging of subsurface structure, as already mentioned, the remote sensing techniques and geophysical technology using both satellite, but also LiDAR, remote sensing like the thermal imaging, the radar to map hash dispersal and so on. And more recently, the drones and light unmanned vehicles that allow to make safe and real-time measurements in plumes on volcanoes when conditions of access are too difficult, and so on and so on. I developed more comfortable field boots for extending durability of volcanology was also a great development. So this 100 years development of volcanology on the scientific point of view, technological point of view, has also been promoted as before by the occurrence of several emblematic eruptions and catastrophic eruptions, different types that promoted a special interest from scientists, volcanology, but also from the governments In particular, this year we have visited the 40 years of the 1980 eruption Mount St. Helens, which correspond to the step ahead in quantitative volcanology. Was one of the first catastrophic eruption directly instrumentally surveyed. And we can mention here, maybe this is, I don't know if it is visible to everyone on the right of that slide, a discovery also of CO2 killing eruptions. The role of CO2 dissolved in lakes or emanating with phreatic eruptions, such as during the Dieng eruption in 1979, or in Lake Meos in Cameroon, 1986. And these events and this increasing, this important activity also happened during a century of a strong growth of global population. In 1920, the global population was less than 2 billion people, and we're now over 7 billion. So this mechanically has increased the risk, the exposure of population to volcanic hazards. And this is also visible here in this graph below, where you see the number of population in terms of the functional radial distance from a volcano, from 0 to 100 kilometers. And this is 1975, 1990, 2000, 2015. You can see how the number of population has increased during these 40 years, sorry, at the functional distance to proximity to active volcanoes. Today, close to 1 billion people are living within 100 kilometers of an active volcano. In particular, this strongly concern the latitudes where people are densely concentrated, in particular Indonesia, here to the right. So, managing volcanic risk has become more and more a worldwide problem. Volcanologists, the challenge for volcanologists in the future will be to make coinciding their capacity to monitor change in volcano behavior, which now is feasible using instrumental networks and our better improved knowledge of volcanic processes, with the ability to interpret this change in terms of eruptions in order to allow an efficient management of volcanic risk. So studying physical understanding of the volcanoes must be translated into hazard assessment, forecasting, and prediction if possible. The risk of catastrophic future eruptions is high, has grown with the population growth and the number of big cities close to volcanoes, including the possibility, as raised by Newell and High in a paper in 2018, of including the VIE7 eruptions with global impacts, such as the Tambora eruption, for instance. Volcanic eruptions remain difficult to predict, of course. It's a very complex process. And volcano monitoring, education, preparedness are crucial to mitigate volcanic disaster in the future. The future of volcanology, based on what we have seen over the past 100 years, there have been a very great evolution from surveying techniques to spaceborne sensors, from reactive response to proactive exploration, from modeling to numerical simulations. And the future developments present or show great hope, great promise, based on new technologies, techniques, and so real-time volcano monitoring from ground and space, automated data processing. This is a new step with machine learning help and with algorithm that allow rapid processing of data recorded by observatories, advanced modeling approach as well combined. To conclude, the IAVCEI, the International Association of Volcanology, today is one of the 8 scientific associations within IAVCEI. It is an international framework for both basic research on volcanoes and mitigation of volcano disasters. Around 1,700 membership now, with many young people and more women. Many research initiatives within IAVCEI driven by research commissions, working groups, and networks. And in particular, IAVCEI hosts the World Organization of Volcano Observatories, the WOVO, which we plan to renew and reactivate in a stronger shape. You have here the list of IAVCEI research commissions. The awards of IAVCEI, a new award is being created for volcano surveillance and crisis management. And this award, I don't know if you can see the right on my side, has been attributed to CVHM and Geological in 2018 for the fantastic job they made over the past 10 and 20 years. So IAVCEI Commission promotes multidisciplinary collaboration and advance to the international committee of volcanologists with different kind of people, group of people, very enthusiastic people with different field workshops, congress, and so on. So I recommend you, strongly recommend you, become a member of IAVCEI. Thank you very much. Terima kasih banyak.
Okay. Thank you, Patrick, for your very nice presentations. So to make the time more effective, I will continue with the next speaker. Will be Mr. Jacob Lowenstern. He is a volcanologist from the U.S. Geological Survey, and he is currently the chief of the Volcanic Disaster Assistance Program at the U.S. United States Geological Survey. Today, Jacob or Jake will present about the advancement, the past and the current condition, and also the future of monitoring system on different countries. Jake, time is yours.
Okay, I am ready. Somebody else has to stop sharing. There we go. Okay. All right, is that working?
Yes, that's good.
Just actually, okay. All right. Well, Salamat Pagi. I'm delighted to be here for this celebration of volcano monitoring in Indonesia. I thank Pak Devy and Pak Hendra for the invitation. And on behalf of the Volcano Disaster Assistance Program, I congratulate PVMBG on its outstanding record of service to Indonesia and volcano monitoring. I was asked to cover the topic of volcano monitoring systems around the world, so I will discuss a bit how we monitor volcanoes and how things vary globally. For those of you not familiar with us, VDAP is funded mostly by USAID with additional support by the USGS, the organization that employs us. Our goal is to assist volcano observatories around the world to reduce the risk from volcanic eruptions and protect people and infrastructure. There are many ways to achieve that goal, including education, outreach, communications products, and careful planning. But of course, it's also critical to have sufficient volcano data so that we can track changes and make informed decisions. That's where instrumentation and networks come in. USAID provides funds for equipment that we can donate to countries that have a clear need. This map shows those countries and volcanoes where we've worked over the last 34 years. And for many years, Indonesia has been a major place for us to work. It's got a huge amount of volcanic risk, and the volcanoes are erupting here, and we all globally learn a lot from what happens in Indonesia. So we hope to continue working here in the future. Now, the other speakers are going to get into some detail on techniques for monitoring, which are summarized on the right in this diagram. I'm going to focus more on how we decide strategies for volcano monitoring. There are some parameters to consider, and I'll go through them in subsequent slides. They include the kind of volcano, be it a caldera, a volcanic field, or a stratocone, whether it's remote or near a city, its geography and nearby infrastructure, the threats from the volcano, and even its latitude. It's important to start off by saying that all countries should design their monitoring strategy based on a careful analysis of volcanic threats and societal vulnerabilities to form the basis of a prioritization. At VDAP, we call these documents threat assessments and gap analyses, and they permit the observatory to decide which volcanoes pose the most threat in their country and what instrumentation is needed to minimize the risk countrywide. This is especially important given that resources are limited even for the wealthiest of countries. Let's talk about some different situations. For example, perhaps we have a large stratocone in a big city. This requires very high quality monitoring. You'd want a full network of seismic stations to locate earthquakes precisely, plus multi-parametric data that includes geodesy, geochemistry, and webcams. You'd want lots of redundancy for data transmission and power. It's critical that the monitoring continue even during an eruption. So you might want some equipment on AC power, but others on solar power and batteries, or even other sources of energy if you have them. Or maybe we have a big caldera where we would also need a considerable network of seismic and geodetic equipment and the ability to separate out tectonic and geothermal phenomena from water that may operate separately from the deep magmatic processes. So you might want additional geochemical equipment or maybe some instruments in shallow boreholes to listen to those shallow phenomena. In contrast, you might have some different priorities on remote islands where much of the risk comes from ash in the atmosphere. The most important thing may be to detect explosions after they've occurred. The easiest way to do that is with several infrasound arrays placed thoughtfully throughout the region. Combined with satellite remote sensing and global lightning detection, this might achieve adequate capabilities to provide volcano alerts to the nearby population and aviation community, and it may also allow simultaneous monitoring of 10 or more volcanoes with minimal infrastructure. Of course, on more populated islands, additional equipment will be needed. Now, how you design a network also depends on what you're trying to protect. Are people in river valleys vulnerable from lahars, mudflows? Could plains fly into ash clouds? Or are nearby villages susceptible to lavas and pyroclastic flows? The equipment you need will partly depend on what and whom you're trying to protect. Another key challenge is the difference between frequently active volcanoes compared with those that haven't erupted for hundreds of years. San Miguel here on the left seems to have few, if any, obvious seismic precursors to eruptions. Instead, summit, tilt, gas discharge, and infrasound may prove more useful to forecast eruptions, or maybe some parameter that we currently aren't looking at. In contrast, closed dormant systems like Mount Hood show abundant precursory earthquakes such that a regional network capable of detecting and locating small volcano-tectonic earthquakes is generally really useful. In countries with limited resources, it might be sufficient to have a single reliable station near each volcano to track the amplitude of seismic activity. But it would need to be close to the volcano to see tremor and the long period activity that's important in terms of magma movement. And you need very clean data streams without a lot of cultural noise to track the time series of earthquakes, energy rates, and frequencies. A little bit about geochemistry. Some volcanoes are open with respect to gas flux, and changes in volcanic gas output may be helpful for detecting a new intrusion and for forecasting volcanic activity. The use of several scanning DOAS may therefore be useful for these volcanoes, as Sinabung on the right. However, most potentially active volcanoes have no significant flux of SO2, so that one or two multi-gas systems may pick up changes in dormant volcanoes in the ratio of other gases like H2S and carbon dioxide that may emerge from less active volcanoes and cooler geothermal systems. And they can also detect the more subtle increases in sulfur dioxide. For real-time monitoring and forecasts, telemetry is critical. Data need to get to the observatory to be useful. Radios have an upfront expense, but they are cheap to operate. Analog technology doesn't require a strict line of sight, and thus can be somewhat forgiving when you set it up, but it is increasingly difficult to purchase this old technology. Digital radios are much preferred for many reasons, but the installation requires a lot of thought to network design to ensure success. It is tempting for many observatories to use cellular modems to take advantage of community infrastructure and to avoid the need to build radio relays and towers. But it's important to consider that the cellular service may not be available during a crisis when everyone is seeking bandwidth and trying to make calls. Satellite telemetry is expensive and energy hungry. Currently, it is the technique of last resort, though it may be practical when there is hardwired electricity available, but not internet. New satellite technologies will improve, but they are likely to be prohibitively expensive in the near term. Latitude and altitude have a huge influence on equipment and station design. In Alaska, solar panels are placed nearly vertically to maximize solar radiation, and huge banks of batteries are needed to keep stations running in the winter. Ice and snow can bury antennas and solar panels. In the tropics, solar panels need to be nearly horizontal to maximize sunlight. Volcanic ash can land on them, causing batteries to fail by blocking the cells in a day or two. Ants and bees may make a home in the vaults, destroying the wiring. Lightning is a peril to electronics. In some countries, vandalism and theft requires impressive fencing to protect equipment. The lower right photo is from Congo, where staff live at the seismic stations and manually place the solar panels outside for charging each day and take them inside at night to protect them. In conclusion, there isn't a standard formula for a volcano monitoring network. What is needed can vary greatly, and this will stay true into the future. But speaking of the future, much of the future of volcano monitoring lies in space and on the internet. Right now, we have open databases like VDAP that can be used to help find analog to current observed volcano behavior, and thus they can help with volcano forecasts using the real-time data. Satellite data from outside the observatory yields information on the gas, ash plumes, meteorology, thermal, and radar. All these global resources add immeasurably to the ability of observatories to optimize information from their ground-based networks to help make informed forecasts. But these global resources are run by diverse communities of nations, organizations, and individuals. And it is possible that these global communities may increasingly expect or desire that the observatories share back their data. For example, I suspect that funding for telemetry, especially satellite telemetry, may be linked to sharing data with international partners. Not VDAP, but other international partners out there in the world. And that means that observatories may increasingly need global collaborations to stay at the forefront of monitoring technology. This will provide the opportunity for new partnerships, but it may result in some loss of control for observatories when others have access to real-time data. Well, that's my 10 minutes. Again, I thank you for the invitation, and I look forward to the upcoming discussion. Thank you.
Thank you very much, Jake, for the presentation. So to make time, we will continue with the next presentation from Pak Hendra Gunawan. So he is the head of volcano monitoring, volcano mitigation in Indonesia currently, and he was studied in France, and his expertise was in the field of geophysics. And for Pak Hendra, the time is yours.
Okay, thank you. Good morning. First of all, I will say it is a pleasure for me to present and talk about volcanology in Indonesia, especially on volcanic monitoring observatory aspect. I will describe briefly some significant development in the volcanic disaster mitigation history, which is basically from the early 20th century. I hope this talk provides a forum for showing the history and the importance of mitigation in a broad sense, and also the impact of volcanic eruption disaster in the region. From the two first speaker, we know about the basic science and the program, especially from VDAP across the world, about the application of the how to monitor, to implement the technology for the volcanic monitoring. As back to Indonesia Volcano Observatory, as background, in the early 20th century,
kalau lama dan naiknya lama, tadi kita IDM-nya emang bentar.
Baron George Escher was a promoter of a volcanological survey before 1919. In spite of systematic geological work started in the mid 1800s. You can see in the left picture above, this is Junghun observation at Lamongan volcano in East Java. At the same time, the publication is more in the late of 1800, especially in Journal Natural Science Netherlands Indies and Journal Transaction of the Royal Academy of Science. Then in 1852 in Bogor, then Batavia, the Netherlands Indies government founded Mine Department, who will work for the scientific work and especially exploration and mineral resources. For the publication, the most significant series of geology publication is almost every year from 1872 until 1939, where the volcanology survey started as a branch from of the geological survey in 1920. As you know, Cloud volcano is one of the most active volcanoes in Indonesia. In this case, in 1919 eruption, Cloud suffered a major eruption. But 1 year before, Escher's suggestion has success to support in 1918 a volcanological commission, then following by Kamil, who was geologist in charge, with first study which was undertaken on some volcanoes of the west coast Sumatra. After some routine survey in Sumatra, but the milestone event was already from program at Semeru for helping the victim of disaster after a catastrophic caused by mud flow, and of course the catastrophic eruption of Cloud volcano in 1919. We have surface studying the type of the volcano, investigation the managed region, trying to reduce effect of an eruption, finding out a possibility of protection, developing a system to warn and evacuate. And I will talk now about the importance of volcano monitoring observatory after 1920. In 1927, Omari seismograph deployed at observation station at Merapi, and then for Papandayan and Clut had the Wichet seismograph. After the catastrophe of Clut eruption, the volcano watching service went to volcano research in 1932, where some volcanoes gathered permanently from fixed observation center as Merapi, Papandayan, and Clut. Then continue to Tangkuban Perahu, Merapi, because catastrophic eruption, and Ijen due to the danger crater water rich in sulfuric acid. Over time of decade, unfortunately, the disaster mitigation program had been organization around more reactive response. But anyway, for CVGSM, over the time, almost have the same for the main task and function. For the conduct research, investigate and surface of volcanology and geological hazard mitigation, issue an early warning for volcanic activity and landslide, disseminate geological hazard knowledge to local government and community, produce the geological hazard map for spatial planning, and especially to give technical recommendation to the local government to do geological hazard mitigation effort. So we can see from the early of 20th century until now, the main task and function of CVGSM is relatively not changed. Especially after the 1988, Indonesian political reform introduced the role provincial and regency government who are responsible for the implementation of mitigation policy agenda, which followed by the Disaster Management Law number 24, 2007, which mandate the central and regency government to share responsibility and authority for disaster management. I present this slide to show the implementation CVGSM implementation for the Clut case in 2014 eruption. This is Clut volcano has experienced at least seven times eruption during 1900 until 2020. 2014 eruption occurred with the quite powerful where spewing of volcanic ash reached at a height of 17 kilometers. This explosive volcanic eruption formed an eruption column and umbrella cloud, where the eruption column transport a large amount of solid pyroclastic and volcanic gases. This is the picture of the left-hand side above, the impact area after the 2000 Clut eruption around the summit. We can see the bright ones deposit. This is the product from the 2014-11. And the picture in the right-hand side, normally I show you the coordination. So I take the picture from the journalist, where we the CVGSM had a coordination with the VNPB and the Regency VNPB from Kediri, Blitar, and Malang. The coordination meeting take place about 10 days before the eruption in Surabaya. In this slide, I will show you a very good example, include eruption case in 2014. BNPB invites CVGSM and Clued Observatory for a coordinating meeting just 10 days before the 2000 Clued eruption. Meanwhile, a good lesson from the 2014 eruption was an experience responding to unrest being closely monitored prior to, during, and in the aftermath of the eruption. In this slide, I'll show you the Clued monitoring equipment in 2014 before the eruption in 13 February 2014. So we had some seismic and deformation data. This is the equipment in the field. And the interesting thing is about the data for the seismic, especially it's 6 hours before eruption. So we can see clearly an increase of the seismic energy just 1 hour until 1 hour before the eruption. At that time, the full CVGSM team at the Clued Observatory was sure about the eruption for the Clued volcano. Another deformation monitoring data 1 hour before eruption have the same clear onset from December 2013 until 1 hour before eruption. At the same time, the Volcano Observatory deploy and maintain other monitoring equipment and assess hazard, coordinating and provide community education, socialization in region around the Clued. As I mentioned, 10 days before the eruption, was to minimize the confusion for volcanic crisis. So finally in the during the eruption, there was about more than 60,000 people evacuated, and there is no victim, fortunately. We are very happy, CVGSM, about the handling of the crisis of Clued volcano. And then after the Clued history, present day, CVGSM have more the 69 monitoring station. Thanks to the new technology, we use the satellite transmission data for all volcanoes around Indonesia. So with this system, we have two kind of data. First, from the volcano observatory in place, and monitoring data in Bandung in CVGSM office. The other aspect is the I will show you how the historical development for the infrastructure, especially for the building for the observatory. In this case, we can see observatory year before 1971, 71st at Ijen until the present day. So the first picture above is before 1971, and then during 1985 until 2011. So we have some change of the infrastructure, and the present day we can see at the picture in the right hand below. And this is another example at Rinjani Observatory, the right hand side, and the Raung Observatory in the right hand side below. So finally, in total, the Volcanic Monitoring Observatory Indonesia, now we have about 74 observatory to monitor for about 69 volcanoes in Indonesia. Now, for this moment, I will thank you for your kind attention, and I hope with this presentation I will give some sight about the many aspects of the monitoring in volcanology. Thank you very much.
Okay, thank you, Mahendra, for the presentation. And the next presenter will be Professor Fidel Costa. He's a volcanologist from Barcelona. Currently, he is in Singapore as associate professor and chair at the Asian School of the Environment. Today, he will give a talk about the geology, petrology, and geochemistry. To Fidel, time is yours.
Okay, thank you. Selamat pagi. I'm happy to be here, the opportunity to talk to you, and congratulations for your 100 years anniversary of CVCHM. The title I was given is to talk about geology, petrology, and geochemistry. And what I will try to do is to explain you how can these tools and these contribute to volcano hazards monitoring and give you some developments. When one thinks about volcano monitoring, one thinks about this picture. When one thinks about how to anticipate eruptions, the same picture that Jake showed probably was done by the USGS. And you see that there's a range of tools we can use to monitor volcanoes. How this data changes with time, let's say seismicity or the formation, is what allows us to say that the volcano is going to erupt. But me, being not a geophysicist, or geologist, I'm kind of stuck in a sense. And I tend to look at something that people are not looking at this picture, which is something in the right side. What you have when a volcano is erupting or has erupted in the past, you have a volcanic history. You have volcanic material, you have here crystals that I have shown here in colors. And just to emphasize that although volcano monitoring is what we use to forecast immediate eruptions, by looking at the past history of the volcanoes and looking sometimes even at the current history, what they're erupting by looking at the volcanic ash, you can also get a lot of insights about the activity of the volcano and also mitigate volcanic hazards. So obviously, by volcanic deposits, we cannot anticipate eruptions because you need something to have erupted to study, but we can actually help to mitigate volcanic risk by answering, for example, the following questions that I have selected. One question that we can learn about is how often is the volcano going to erupt, and what is the likely size of the next eruption. We can also learn about what is the structure below the volcano and what processes led to eruption. This is one of the main problems we have on volcanology. We cannot see below the earth. So we are always trying to figure out what's happening with the volcano, how things are moving, is the gases coming out, or is the smells that come out. So it's a major problem we have in volcanology is we cannot see inside the earth. And I think looking at rocks and minerals can help us to see what's below the earth. And then something that it's been increasingly apparent is that ash, looking at volcanic ash, can help decide how is the volcanic eruption going to evolve. Although the volcanic eruption might be already started, one of the main problems on dealing with volcanic crisis is how is the eruption going to progress? Is it going to be bigger, smaller, etc. So I have selected some data and information that addresses this, mainly from examples of collaborations we have between EOS, ASC, and CBTHM, which actually we've been collaborating, I just already. So how do we learn about what is the likelihood of volcanic eruptions from a volcano and the sizes? Basically, the sentence is here. So the past is the key. So we're looking at doing fieldwork, mapping, and dating. How often this volcano has erupted, how big there were the eruptions, and from there we can calculate the probability that a volcano will produce an eruption of a given site. What are the challenges that we have? You know better than looking in Indonesia, tropical country, there's a lot of vegetation everywhere. So there's a lot of concerns or a lot of problems we have to solve in terms of see what are the past deposits, how thick they eroded. It's a populated country, so it's also a lot of vegetation and deposits that have been moved to people that are living there, because volcanic deposits are also very useful for people. And so here you have some of the images that we were doing together, the field work in Gede volcano. So this is one of the images, one of the maps where we work in Gede volcano. And what you see these different colors is that before this, there was only a general understanding how many times had Gede volcano erupted, which by the way is south of Jakarta. It's not too far from Bandung. And a lot of detailed work. Here you have on the right side the plastic flow and below of a lots of discussions in front of the outcrop. To this side, is this a lahar or this is the paraplastic flow? But after many months of work, we were able to work out what you see here, which is a stratigraphic column that summarizes the eruptions that this volcano has done and when they have been done. And so we can say from this data that in the last 10,000 years, there have been at least 4 major eruptions. Here we used VEI 2 or 4, which is, you can see it as an analogous to earthquake sizes. So it would be VEI 2 eruption is smaller than the VEI 4, and the largest one is VEI 7. So we know that this volcano has at least had major eruptions in the last 10,000 years. So this gives us an indication if Gede volcano were to reawaken, what would be the expected size of the eruption. And this type of information, what is happening in the future is that we doing databases of how often have these volcanoes erupted, and we putting this information in terms of a probabilistic. And this is an example of what we call an event tree, where by looking at the numbers of eruptions, the types of eruptions, and doing statistics, we can say, for example, again, if this volcano were to erupt, what's the likelihood that it will be of a given size, and what's the likelihood of the types of deposits that will it produce, and what's the likelihood probability that it will reach a given sector. So the next important question I want to talk about is what I was mentioning. One of the main problems we have in volcanology is that we don't see below the volcano. Here you have in the right-hand side a diagram with Caroline, who is the Maisonneuve, who's also working in Singapore and main collaborator, where she has drawn here that a volcano and several processes that can happen in the upper part, volcanic conduit, where you can have domes and explosions. But we are always wondering what's happening below, what's happening in what we say the magmatic reservoir, where volatiles that are accumulating, is the pressure increasing, are there new fluids coming below the volcano that might trigger an eruption? So by looking at the deposits, by looking at the crystals and the minerals and doing some thermodynamic modeling, we can know where is this magma, what processes led to eruption, and in what time frames. And so this is a relatively kind of straightforward procedure that we have been also doing with working together with IAVCEI, where we take a hand specimen, we make thin rock sections, we can observe them under the optical microscope or under the electron microscope. The image of the been doing together with VDAP in Yogyakarta, where they have an electron microscope, and we have been working together to identify the positions, and then make models, thermodynamic kinetic models that tell us where is the melt and when the volcano may erupt next. So an example from a project we have together between EOS and IAVCEI, the volcano of Marapi in Sumatra, and this is some examples of images of electron microscope images of crystals for Dini Nufani, who's doing a PhD with us and with Caroline, where she's been able to look at the different minerals and propose hypotheses of what's happening below the volcano. Some of the challenges is that it's difficult to have a unique answer, more than one answer that put data, and that the volcanoes change over time. It can take thousands of years, or it can change very quickly before eruption. So just to show you a little bit how we do this, here you have three schematic diagrams. In the right-hand side, you have the mineral compositions. You have different gray colors, which show different compositions. And you can see that these crystals have something like 3 rings. So the crystals are recording the changes of conditions. And the art here, or the interesting part of these studies, is that we take these different parts and put them on a sequence. We put them on a sequence of events, and we make a time history. And by calculating the pressures, we can make a time history of what the processes are happening below Merapi volcano. For example, here you see that Dini proposed that the main magmatic reservoir below Merapi is 20 kilometers. So having this information is critical to be able to interpret data. For example, is the seismicity happening shallow or deep? We can understand better where the liquids and what processes lead to eruption. In addition to this, one very important thing that is for hazards management is the time frames. Time frames are the ones that tell us what is the emergency planning that we need. And so crystals, by studying the crystals, and here you have some examples of what we call clinopyroxene crystals, we can do kinetic models, we can do models that expositions, and from there, we can know something of the time. So the times of these crystals tell us, for example, when the magma came below the volcano and then erupted. So the timing between new magma arrival and eruption can be useful, for example, if we start seeing magmatic unrest, when we can expect that the volcano will erupt. These time frames, here's 2 examples from 2 crystals. One crystal in the left side, it says 6 days. The other crystal on the right side, it says 1.5 months. And so these types of times we were getting after, because they are very useful to plan emergency planning. In one case, in the left side, you would say we have very short time to get ready. In the right-hand side, it would mean we have much more time. So this is how crystals can be some hazard mitigation measures. And as a perspective, what we have been doing is that depending on the tools we use, we can see different things. And so we can see deeper, we can see more detail, we can do better estimates. And one of the things we've been doing in Singapore with Rico Made, who's actually also originally from Indonesia, from Bali, is to look at techniques to go to the nanoscale. And this is here 2 examples of nanoscale determinations of mineral compositions that can actually give us further insights and more details about what are the pressures and the times that lead to the eruptions of the volcanoes. And finally, another topic I would like to discuss is, although we have to wait for these eruptions to happen, once they start happening, we have a chance to sample them, sample the volcanic ash, and see how the volcano is progressing towards a change of dynamics. This is an example of activity in Merapi volcano, 2012 to 2019, that it shows that it has different types of activities. You have eruptions, you have some dome formation, you have bigger explosions. Although the volcano has something, we want to know, is it going to go to much bigger eruption? When is it going to finish? And actually, I think that doing sequential sampling of volcanic ash and classification of the different components, we can understand better if, for example, these eruptions are just related to shallow hydrothermal system or new magma coming into the system. Similar to when we were looking at the minerals. And again, here on the left side is the scanning electron microscope in Yogyakarta. And if we do a sequence, this is the sequence of flow that we use. And the key thing we want to do is find the different particles. Juvenile particles, which just means juvenile is the new magma deep. We have lithic particles, which is just part of the rock fragments around the volcano, and hydrothermally altered, which might. So by looking at the changes of proportions of these particles, and this is just one example, this is not from Indonesia, this is from Chile, that I will not go into detail, but the different panels here are how the changes in volcanic ash particles have changed and compare it to, for example, the seismicity. And we can start to correlate changes in volcanic gas particles with the seismic data, and this better what is happening below the volcano. Are these explosions just due to accumulation of volcanic gas, shallow magmatic systems, or is it a new magma intrusion that is pushing the rock from behind, and we're looking at a scenario of a much bigger eruption? This is the type of question that I think we can develop much better together with CVCHM. Challenges is that these are not so easy to classify sometimes. It's equity because we can do a given number of measurements, different types of particles. It's hard to decide, are these juvenile, not juvenile? And this change between volcanoes, it might change between eruptions. So it's not straightforward. And this is, I forgot to mention, this is results of a student, Damia, who's having a database of volcanic ash particles and using artificial intelligence to classify the particles and in near real time. So we think that in the future, this should be also possible. Summaries and of course, to use geology, petrology, and geochemistry for hazards mitigation, we can answer some types of questions that can give decrease the hazards of volcanoes and risk. We can produce, by doing field work, baseline of probability of eruption and the size of eruptions, where the magma is and what processes have led to eruption and previous eruptions. And we can also track the real-time changes of the eruption if we look at ash particles. And maybe not much use. For volcano monitoring, we focus on geology and geophysics, and this is great, and we need to do this, but looking at the rocks is a really complementary way to look at it, and it gives us a much more robust understanding of what is causing this eruption and what is the volcano going to behave. And finally, just to say again, emphasize, I'm giving this seminar for you, for CHM. Happy anniversary. Congratulations for your excellent work and saving lives. Keep doing it great. And I hope we can continue collaborating in the future. Thank you.
Thank you, Fidel, for the very nice presentation. As we still have two presenters, let's move on to the next presenter, which will be Professor Masato Iguchi. He is a volcanologist from Japan. He works currently at the Sakurajima Volcano Research Center at the Disaster Prevention Research Institute at the Kyoto University. He managed to survive from the latest typhoon Haishen. So he will give us a lecture about volcanoseismology. To Mr. Iguchi, time is yours.
Okay, thank you, Devy. Thank you for inviting me to the 100 years anniversary of CVGHM. I'm very happy to talk with you. So I try to just this one. Oh, yeah. I try to talk about just the seismology for the essential method for the volcano monitoring. So, okay, why? Okay, firstly, I talk about what is the volcanic earthquake. It is very difficult to define what is the volcanic earthquakes. Of course, this is the figure from the USGS. Of course, there are many seismic events near the volcano and below the volcano, but it is very difficult to say what is the volcanic earthquakes because one is the disability is most difficult because some of the really tectonic and some of the related with the volcanic activity. So we just say the volcanic earthquake, the seismic event near the volcano. Why we use the seismological method for the monitoring volcano. So the one is the advantage of the seismic method is a long-term history. At least the seismic method has a history of the more than 100 years. And the second one is this is why we can continue for the long term, the easier maintenance for the continuous monitoring. So the seismology, seismic observation is that this is a very simple method. So it is very easy to maintain for the volcano. And various analysis methods is available to analyze the seismic records. This is very important for the further development of the seismology. And the second one is very important. The seismological observation could be a trigger of the upgrade volcanic alert level. Volcanic alert level is very important, but when we will upgrade the alert level, what's the data supports the upgrade alert level? So considering about this, the seismological method is a very easy. Of course, not so easy, but the more effectively to make decision to the upgrade alert level. But for the maybe that this is for the volcanology, disadvantage of the seismic method. The earthquake is generated by the shear fracture. Most of the tectonic earthquake like this. The volcanic activity cannot be described only by fracturing. So I just pick up the three important parameters: location of the hypocenter and source mechanism and seismic energy and their time series. And the seismometer is a very simple. The mechanical type is this is a mass and spring and damper system. This is a very simple method. And in old days, we have seismometers. For example, this is the Aso Volcano Laboratory. Operated nearly 100 years ago. And this record is this signal is recorded on the smoke drum paper, And in this type of the seismometer, we can record displacement. But now we use the electromagnetic type. The electromagnetic type is also the mass and spring system. But this movement of the mass is measured by coil in the magnetic field. The voltage output from the coil is proportional to the velocity of the coil. So, and also the damping resistor is act as a mechanical damper. So such a voltage output system is very helpful to improve our monitoring system, because the amplification and dynamic range and is data transmission and such a electric magnet type seismometers essentially support the present seismic observation system. And this is the variety of waveform, the volcanic earthquakes and tremors. Maybe the volcanic earthquakes has a variety of seismometer waveform, but and names are very different. The name volcanoes and volcano. But here I just divided into the two types. One is a volcanic tectonic earthquakes, and second one is the other type of the volcanic earthquake. And just simply explanation, the volcano tectonic earthquakes is a very simple waveform. Just the P and S wave and P and S wave time interval, how to close the hypocenter of the and this volcano tectonic earthquakes is generated by the shear fracture of the rock, because the magma intrusion pressurized the fracture area, and fracture suddenly occurred. The source mechanism of the double couple. But the other type, I say that this is a rare volcanic earthquakes. Sometimes we call the low frequency and long period B type, or sometimes the various variety. But essential that this is a low frequency and concentrated in the narrow zone. On the other hand, VT earthquakes disperse the wide range of the volcano, but real volcanic earthquakes, such as low frequency, long period earthquakes, concentrated in the narrow zone related to the magma activity. And also, such a real volcanic earthquakes, the volume change sources. This is very different from the volcano tectonic earthquakes. Volcano tectonic earthquakes is just measured, generated by the shear fracture, but real volcanic earthquakes, the volume change, sometimes the expansion and sometimes the contraction of the gas-rich fluid. And this is a very typical transition of the types of the volcanic earthquakes. This is firstly, we started at the rest stage, and earthquakes seismicity suddenly increased by the volcano-tectonic earthquakes. The volcano-tectonic earthquakes is followed by the volcanic earthquakes, sometimes low frequency earthquakes, long period earthquake. And then the volcanic eruption occurred. Related to volcanic eruption, the many volcanic tremor and eruption or explosion earthquakes. The right figure is an example of the Utsu 2000 eruption. Started with the VT earthquakes increase and followed by the low frequency earthquakes increase. And how to explain this? The firstly, intrusion of magma, and intrusion of magma shows the extension field, and this VT earthquakes occurs at the lower, deeper part. And then magma can move up to the shallow part, and suddenly degassing occurs caused by the decrease in pressure. the degassing is the important parameters for the generate the volcanic type. And then the sum of the shallow VT earthquakes, maybe the hypocenter system, maybe like this, the deep VT earthquake system and the shallow VT earthquake system and volcanic earthquake system, the concentrated conduit. And this is the focal mechanism of the volcanic earthquakes. I have already explained this one. The second one is we would like to forecast the hazard of the volcanic eruption. How to evaluate the hazard? Hazard evaluation must be based on the forecasting the eruptive volume. Eruptive volume and seismic precursory seismic energy is have some relation like this. This is the database from the database, and some of the Indonesia of volcanoes are plotted here. The prefix M is a Merapi, and this is the Merapi 2010 eruption, and some of these Japan volcano. And there is some limitation of the upper limit of the eruptive volume related to the seismic energy. This is very important. We can estimate the upper limit of the eruptive volume from the seismic energy. So so it means that we can evaluate the hazard by the volcanic ash or the pyroclastic material. This is the case to the application to the 2010 eruption, the Merapi. And the change of the focal mechanism of the VT earthquake is very important. Especially we have the three kind of the focal mechanism, as you know, the strike slip and normal fault and the reverse fault. But usually in the volcano, some of the strike slip earthquakes dominate around the volcano. But if the magma intruded in the volcano, the normal type earthquakes dominate. So the detection of the normal type VT earthquakes is very important to the detection of the intrusion of magma. And also the how do we interpret the VT earthquakes? VT earthquakes are quite similar to the tectonic earthquakes. This is the simple conceptual model. This is the relation and differential stress and strain. So the strain is stress is increased on strain is also the increased linearly. So that this is we call this this is the elastic deformation. So the after that, the fracture suddenly occur. So this is expanded to the time series. So the magma intruded here, and so the stress increased, and also strain increased. But the fracture suddenly occurred. So the before the first fracture occurs, this is the stress and strain, the linear relationship. So that this is only the deformation occurs, no seismicity. But after this, the seismicity suddenly increase related to the threshold of the fracture. So the we have the aseismic deformation and also the co-seismic deformation. This is the example of the aseismic deformation and co-seismic deformation. This is the case of the long-term case of the 2010 eruption Merapi. We recorded 17 months aseismic ground deformation and 1 month the co-seismic ground deformation. And the right side is a short-term example of the Sakurajima eruption, started with inflation without seismicity, and this is followed by the increased seismicity. And also, our seismic method is useful to evaluate the mass eruption rate. So the mass eruption evaluation of the mass eruption rate is very important to evaluate hazard, how to disperse the volcanic ash widely, so that it depends on the mass eruption rate. So that we need a technique to the mass eruption rate by using the volcanic earthquakes or the ground deformation. Because seismic observation and ground deformation is a robust method for the monitoring volcano. Thank you very much. Thank you.
Thank you, Mr. Iguchi, for the very nice presentation. We have one more presenter, so we will continue and move on to the next presenter. And our next presenter is Professor Dr. François Beauducel. He is a volcanologist from France. Currently, he is in Yogyakarta. So he worked a lot in Indonesia, and from 2016 to now, he is a senior researcher position at the Center for Volcanology and Geological Hazard Mitigation of Indonesia, with a research project mainly in improving observations and modeling tools for volcano monitoring at Merapi volcano and also North Maluku province. And today he will present about the deformation techniques. And to save time, please, François, time is yours.
Oke, terima kasih Pak Devy. Saya lanjut pakai bahasa Inggris ya. Okay, good morning everybody. Okay, I don't know if you see my presentation now.
Yes, we can see your presentation.
Okay, thank you. So I will just explain you the deformation method and start with the question, why does a volcano deform? In fact, a volcano deform, there is no deformation usually when there is a volcano at rest. And the deformation will start when there is an input of magma from depth. So we are looking here at the last 10 kilometers of the upper part of the volcano. And the input of a deep magma will make the volcano inflate like a balloon, and we then are able to measure a global inflating, ground deformation upward at large scale. And after that, the magma will rise to the surface and fill in the shallow magma chamber, increasing the pressure inside, and then we will have some more higher deformation, but more local inflation. And then, when the volcano is erupting, when the magma came out with explosion or lava dome or lava flow, usually we have deflation because of the decreasing of the magma pressure inside the deep or even the shallow magma chamber. So the principle is quite simple, and you understand that the magma movement inside the volcano will induce pressure variation in the reservoir, and then the volcano edifice will inflate or deflate before or during eruption. But at the scale of the volcano, this is usually only millimeters or even centimeters displacement, so it's not visible and not detectable by human. So the objective of deformation studies are to make some observation and measurements on the volcano, make some measurements on the volcano and interpret them through modeling. I will explain that at the end of my presentation. And the modeling will give access to two things, imaging structures inside the volcano, like a tomography, look at the magma chamber, look at conduits, or even the discontinuities, the fracture inside the volcano. And a second output will be to quantify processes like evaluating the location of the source, the depth, or the volume variation, or pressure variation, and even to follow in time the magma flow rate. So the main challenge of deformation studies, it's the same as other methods, it's to anticipate eruption, understanding what is inside the volcano and anticipate eruption. But we have to face a major problem, geodesists have to face a major problem, is that there is many different techniques in geodesy and ground deformation. Some are giving good spatial image of the what we call a deformation field, and some other are measuring only at one point, but will give a nice time series of the deformation. Another problem that we have to face is each technique all the techniques are covering only a small part of the time scale of processes. So in this graph, you can see from second to century, and each technique, seismology is able to measure also ground deformation, as Paiucci said, but all techniques are covering only a part of the time scale of processes. So geodesists have to integrate multiple methods and deal with advantage or disadvantage of each of it. So I will describe just 5 main methods used in deformation. And the first one is probably the simplest one. It's to take photos. It can be done by a station on the ground. Station on the ground like here, but it can be done also by a drone. So it's only sensitive to very large deformation, but it is very useful, for example, to follow, like here, to follow the dome growth with 10 centimeters or meters of displacement on the lava dome growth. The problem is that we need direct visibility, so no clouds. A second method, very useful, it's the slope distance metry, what we call EDM, electronic distance measurement. You install on the volcano only small mirrors, geodetic mirrors. You can install many of them, and from a fixed place, you measure the distance using a laser. This is sensitive to centimeter of displacement. So it's adapted to large deformation. It's a very robust monitoring method, very useful, especially on a high explosive volcano. It's easy to maintain, but again, you need the direct visibility without clouds. A third method, it's one of the oldest one, it's tiltmetry. So a tiltmeter is basically, today, it is a bubble level, a spirit level with electronics. And as you can see on this graph, it has been used, it's here at Kilauea, to follow the cycle of inflation and deflation between each eruption of the volcano. So it's very sensitive to the volcano breath, as I explained in the first slide. It's also useful to follow in time. This is one day of deformation at Piton de la Fournaise. So before each eruption, there is some deformation measured by tilt. So a tiltmeter is measuring basically a microradian, and 1 microradian is 1 millimeter elevation at 1 kilometer's distance. So it's very sensitive to small deformation. And the problem is that it's subject to thermal perturbation, except if you are able to install it in a borehole, but it needs heavy means. Another method is GPS. So it's not the same GPS as in smartphone. It's more sensitive. It's sensitive to millimeters absolute displacement. It will give some 3-dimensional displacement on the volcano. You can install permanent station. It will be sensitive also to large deformation. The problem is it needs post-processing, and it depends on satellites and some data from the internet. A last method, as mentioned already by Patrick, is remote sensing from satellite. So this technique is very powerful because it uses radar, so it can go through the clouds, and you don't need to install anything on the volcano. So it's very adapted to remote volcanoes like Indonesian archipelago, and it gives beautiful image of a displacement, like here in Mount Agung. It's sensitive to very small deformation, a sub-millimeters deformation, but the problem is not real time. It needs complex processing, and it depends on satellite programs. So you need to wait the satellite pass to get some image, and we have also still some problem with the tropospheric artifacts, so the effect from the atmosphere. Okay, so what we are doing with all this data, we are doing some modeling, and Patrick already mentioned one of the simple model discovered by Mogi 60 years ago, and it still works. So this model is very simple. It's the idea to approximate a magma chamber as a virtual point, expanding point, a small sphere, into a flat homogeneous Earth. So it's very far from the reality, but it works very well. Simple equation, and as you can see on the right here, on one volcano, this is the data on the left, the data measured by a radar, ground deformation, and on the right, it's the model given by this very simple point source model. So very similar, and we are also able here to example at Merapi volcano. You can see, I remember last year, we were able with this simple model to locate the source of inflation inside the volcano and to estimate the volume. And on the right, it's at Mount Agung, also to estimate the volume variation. Here is the deflation just after the eruption. So it gives a very good idea of the source location and the volume variation. Of course, we are able to make more complex modeling. In 3D with a very complex source shape and the geometry. So this is only some example of what we are able to do with the deformation field. Again, to be able to understand the process inside the volcano and to estimate the parameters like pressure and volume variation inside the volcano. So as a conclusion, deformation method will help to look at the volcano interiors to get the structure inside, the magma chamber, the conduit, to estimate the pressure source location, the volume also. There is many different methods, various advantages and various difficulties also. And like all other geophysical and geochemical methods, it's very useful for monitoring. The future challenges are improving sensor sensitivity and to get new instrumentation like optic fiber and more remote sensing as it best fits the problem of monitoring. Improving artifact removing also the problem of troposphere or thermal perturbation on altimeters, and make more modeling, more realistic rheology, and towards real-time modeling for better monitoring, and of course a more pluridisciplinary integration. As until today we are not able to make a full pluridisciplinary integrated modeling, integrating all the techniques used for volcano monitoring. Thanks very much.
Thank you, Francois, for your presentations. From all the presenters, we could see that there have been so many improvements in the science of volcanology, and mainly this is how volcanologists work to save lives and to mitigate the risk caused by volcanic eruptions. So we still have like 10 to maximum 15 minutes for questions and answers. We have already selected some questions. First, maybe global questions. I mean, it can be to all the presenters. There's a question, can you describe some innovations in volcanology that change this science significantly that it makes it capable of saving lives. So first of all, I would ask all the speakers to turn on their videos. Okay. Maybe Patrick, you want to answer the questions?
You mean the question? The question, if I understood well, is how now volcanology can work well to save lives, something like that.
Yes. What are the innovations? Some important innovations in volcanology that change this science significantly, that it makes it capable of saving lives.
I would say a very prudent answer. We face volcanic eruptions. I mentioned very complex processes, but and also the volcanoes have their own identities. Some volcanoes belonging to the same category, same class, can behave differently, or one volcano can display a wide spectrum of eruption. So we, as Fidel also outlined, we don't have a direct viewing of what happened and the volcano, in contrast to our colleagues in weather forecast. So we are using, let's say, sounding methods, and based on the progress in our understanding of volcanic processes, magma behavior, let's say, magma properties and magma behavior, on some classes of volcanoes, in particular on open conduit volcanoes. I would cite, for instance, Piton de la Fournaise in La Réunion, who tend to behave repeatedly in a very recurrently in a very similar pattern. It's now almost 100% success in predicting eruptions, let's say within a few days to few hours. This is one exceptional case. You have more or less the same success on Etna. For instance, since the infrasonic network acoustic sensors have been installed on the volcano 2008, they got success to forecast eruption from acoustic signals, from infrasonic signals, for 56 among 58 eruptions. So that's very high rate of success. So on some volcanoes, let's say open conduit volcanoes and fed with magma with relatively low viscosity, we now are in position to really well forecast eruption. Much more difficult, of course, much more complex for volcanoes with more evolved, more viscous magmas and longer repose time, for which we have a greater variety of, let's say, unrest patterns and eruptive patterns. And as Fidel illustrated, the history from told by the crystals, studying the crystals and the lavas, indicate complex storage systems, mixing. We have also information from INSAT data now for 240 volcanoes who demonstrated, detected deformation. Let's say 44% of them actually erupted within the last 10 years, but 50% didn't erupt, and 6% erupted without ground deformation. So just to illustrate the complexity of forecasting eruption to save life.
Okay, thank you. Are there any other answers or some other informations from the speakers? Or shall we continue to the next question? Okay, let's continue to the next question. there are several questions here, but one of the most interesting things is maybe what strategies need to be carried out and developed in the world of volcanology regarding the conditions of COVID-19, like now. For example, like this is because volcanoes do not recognize pandemics. There could be eruptions around the world, and there should be responses, and yeah, not only for crisis, but also for like seminars. We have delayed seminars for many occasions, and so are there any strategies that you from different countries have been made to respond these conditions? Please, maybe Jake, you want to answer this?
Sure. I guess I could say that a lot of what we do as volcano scientists is something that we can do without needing to be in a crowded room with people. We have equipment in the field. We can send out drones. So we can react and respond to volcanic eruptions at any time. And we just need to obviously, the way that we go about our field work is slightly different. I know that in our organization, the rules for taking helicopters right now are very different than they were a few months ago, and that we have to be very careful. We have a different rules how we go about doing field work, but we're still doing field work, and we would still respond to volcanic eruptions as they happen. And so I think that in general, we can continue as volcanologists doing our work pretty well.
A compliment, maybe just a compliment from my side. We, unfortunately, from the IAVCEI side, had, as you know, we had to postpone our international meetings that were planned in 2020, postponed to 2021, and even for a scientific assembly 2022. So one major result is that probably we hope to be able to have meetings in physical attendance next year and the year after, but probably we'll develop online meetings as well, part of online meetings. And second and last comment, I'm very happy that during this very difficult time, we didn't have to face major volcanic eruptions requiring massive evacuation. It would have been really complicated to manage.
Yeah.
Okay, thank you. Maybe Pak Hendra would like to, because at the moment in Indonesia, at least at any given time, you have at least 2 volcanoes erupted every day. How you deal with this, Pak Hendra? You have to send teams to the field, while of course the team has a risk to get with the condition of COVID-19.
Kita pakai bahasa Indonesia saja.
I think in English, because
English.
the audience is international. I saw some audience from different countries.
Okay. Right. So it is true. Now it's very hard for us to send for the quick response team or for the maintenance team to the field because the COVID-19. But anyway, sometimes we have no option to avoid to release the problem. So for us, finally, we should have a compromise. So the team should use the very tight protocol to the field, and then For example, we do some rapid tests before or after from the field, and of course, in our office, we use 25% present for the staff. So this is all of thing is to compromise where the monitoring still continues doing, and in the same time we use the protocol for the COVID-19. Maybe.
Okay, thank you, Mahendra. Are there any other additional comments about this?
Maybe to say that what you're doing now in terms of seminar, example of how to deal with the situation. We have 250 people listening. That's great. I don't think we would have so many people listening would be in a normal, in a physical room. They wouldn't fit. So I think there's, of course, lots of negative things, but some things that are also being positive, such as the wider, it seems to me, distribution of talks and seminars and things like this.
Yeah, especially you were working in the university. How you deal with this? I mean, change this will be the new semester, and how you deal with this situation.
Yeah, so we deal with it like we have lots of things that are online, and typically it's real time. It's not pre-recorded, depending on the size of the class. For less than 50 people, we can still do physical, but it's not compulsory. So some people are at their home, and they're taking classes by distance, and others that wish to attend physically, they're also. I guess the challenge there is that when they're physical attendance, you have to ask, and we have upgraded microphones, cameras, and lots of different things to make it work. But it's certainly, yeah, I guess challenging, but I guess some positive things. And also working, for example, with the PhD students, we learn more how to share documents and work at the same time. And so that's another way of, we didn't explore so much this possibility. It's quite effective also to do.
Okay, thank you, Vidal. Maybe let's move on to the next questions. There's a question specifically to Iguchi-san. So there is a question about how people in Japan adapt and responses to volcanoes and their eruptions. What makes people ready to volcanic eruptions, and at the same time could live in harmony with volcanoes? How you deal with this, and maybe this can be also answered by other speakers.
Yeah, thank you, Devy. I think such a situation is Japan and Indonesia is the same, because many people live near the volcano. So the important thing is preparedness of the local government. So in Japan, the local government has the plan of the countermeasures. Individual. This is collaborated with the national government, but the local government has their own plan of operation for the countermeasure. Of course, volcanologists must be collaborate with the design of the plan of operation. Thank you very much.
Okay, thank you. Are there any comments from other speakers? Okay, let's move on to the next question. I think this is quite for everyone. So there is a question about the volcano monitoring network in the world. Could it be accessible to all countries in the same accuracy and resolution? And so this question means that, is it open for other countries, or there are some procedures that we need to solve before sharing this data? So everyone can answer this, especially those who works on the observatories, maybe Jake and Hendra and also Francois. Maybe Francois can answer that how it works in the in France.
Yeah, we are sharing in real time most of the data, monitoring data for Piton La Fournaise and in Les Serentides, La Soufrière and Montagne Pelée. So you are free to access the data from the volcano in real time. But they are raw data, so you have to process them by yourself and interpret them. If you want to get the interpreted data, you just read the public report and so on. But in France, we are sharing the data in real time, especially the seismic stations. You can access them for the active volcanoes.
Okay, are there any comments from other speakers about this data sharing policy?
Yeah, okay. I will try to respond to such question. Basically, the government should open the data, but in this case, we should specify about the purpose demanding of data. In our protocol, in our office, normally the public can send a letter to the head of the CPGFN about the data, and we can cooperate to process and analyze this data. In many cases, we offer many to university, and can be some subject for the dissertation or scriptsy, so or thesis. I mean, so there's no problem for the data. The public can send the application to our office. Thank you.
Okay, thank you, Mahinda. There is we are out of time, but I think we try to add more time, maybe 5 minutes. So maybe this is we have a question from maybe to Francois for this time. It's about how to make difference between deformation due to hydrothermal effect and deformation due to magmatic effects.
Yeah, I already answered the
question
on the web, but very quickly, yeah, it's not possible to discriminate the source. Deformation is sensitive, ground deformation is sensitive to any change of volume inside the volcano. So it can be from magma, from gas, from hydrothermal, water vapor, or anything. So that's the reason why we have to integrate multiple techniques if you want to know what is and to identify what is the source of deformation. Deformation can only quantify the volume variation and quantify image in the volcano interior, but not to identify what is the source, exactly the source of deformation.
Okay, thank you. I think we will have only one more question because of the time. So this is the question for everyone. So what do you think about the state of the art of volcano monitoring at this moment? What do you think is missed from what we have now, and what we should get in the future, and especially how do we deal with the with the people? Because maybe the science has grown so much, but Earth to make the volcanology to say that how to earthing volcanology to people is still a challenge. And so how do you think about that? I think this is a question for everyone. Maybe in global perspective, Patrick can give an opening.
Yeah, briefly, globally, we ideally we wish and we plan to rejuvenate, redynamize what I mentioned and called the World Organization of Volcano Observatories, in the sense that they could exchange, interact, and exchange data and interact much more closely for data, for experience, for so many things, for training, and of course through the famous VDAP, whose Fidel is in charge, and also this intuitively, this leaves open the question of open access of data, with protocols with rules to be, guidelines to be defined, reciprocal assistance between observatories in case of major emergencies, and training, of course, and also better, faster processing, data processing of using machine learning, but also, for instance, satellite imaging. Satellite images are quite accessible. The problem is many observatories do not have the staff, enough staff, trained or enough staff to process the data themselves. So a lot of reorganization at international level could strongly help each observatories and the network of volcano observatories worldwide.
Okay. Others? You can start.
Hmm?
Yeah, you can start without me mentioning all of the speaker names.
Yeah, I mean, this is Jake, and
Yeah.
I agree with Patrick that international collaboration is going to be a bigger and bigger part of what happens. There's going to be more coordination amongst observatories and IAVCEI, and the satellite community, I think, is going to get more organized and try to create products that are more readily available for the observatories. So I think that that's going to be a bigger and bigger thing. But obviously, though, the decisions are local, and so the observatory has to maintain some control over the decision making, and that involves the international community needs to know. Basically to support the local volcano observatories and to have mechanisms so that they can do that without interfering with the important jobs that those observatories do. And the last comment I'll make is that we are getting better and better at understanding volcanoes, but forecasting eruptions is still very, very difficult. And there's always going to be ambiguities and uncertainties. And so really one of the critical things is developing partnerships with the locals, people who live around the volcanoes, the emergency managers, the different government agencies responsible for safety, and getting good collaboration and coordination with them, because they need to be able to work with the people to make good decisions. And the scientists just have their role, but that's just one part of the system of keeping people safe.
Thank you. Are there any more points from the others that would like to be? No? Okay, if no, then it's the time to end this webinar. So thank you for all the speakers for sharing their thoughts from different specialties and from different perspectives. We hope that we could invite you again later and in a longer sessions and in more detail or specific topics. And before we end this webinar, I would like to inform all the participants that at the end of this webinar, we will share the but first of all, I would like, there is an information from the committee that tomorrow we will hold a blood donation event at our office. So, and it will be at 9 a.m. to 1 p.m. And you can follow this link to register. And we will use safety protocols of COVID-19 for sure. And that's for tomorrow session. And for all the participants who asked for the certificate, we also first we will. This is the door prize winner for this for today's webinar. So there are 6 winners, and to all the winners, please contact this email shown on the screen, and say your name, and you are the winner of this webinar session. And last but not least, this is the e-certificate registration. If you need a e-certificate, you can register through this link, and also after you register, of course, you can download it. But if you don't register, then you cannot download it. And all the presentation files is located in this link. So the presenters have already shared their presentations. And this for this e-certificate, it can be requested only up to 1 p.m. It means 1 hour from now, and that link will die after 1 hour. So and if you need or assistance on the presentation files or contacts to the speakers, please contact our contact persons. There are 3 people here. And we only, and this question and answer regarding this matter only available for 24 hours after now. So thank you very much for your attention, and we will see you again later on other webinar. And we, as CVGHM, would like to thank everyone who have joined this webinar, and good day for everyone.
Good day to you.
Thank you so much. Thank you.
Thank you so much. And good anniversary.
Thank you. See you.
Terima kasih banyak. Thank you.
Terima kasih banyak.